everyone, and welcome to today's webinar. Thank you for joining us. Today you will be learning from our expert, Albert Rodfalk, about how to further optimize your radiometric mold level measurement system. I would like to introduce you to our presenter. Albert has a background in chemical engineering. Before joining Berthold, he spent 10 years as an R&D manager developing measurement equipment for the ferro and non-ferro industry. Albert has been with Berthold for 5 years now, working as a product manager, further developing and promoting our wide range of products for the steel industry. After the presentation, there will be a question and answer round, so any questions you may have can be entered to the chat or Q&A function, and they will be answered by Albert directly after his presentation. Also, a recorded version of this webinar will later be available on our homepage. So now I will pass over to Albert.
Hello everybody and welcome to this webinar. My name is Albert Rodfalk and I will be your presenter here today. I expect the presentation to take about 40 minutes and that should leave us with sufficient time for answering most of the questions. This webinar will be recorded and then later downloadable from our website. Before we go through the agenda together, I would like to give a brief background about myself. I have a background in chemical engineering. For the last 15 years, I've been working with development of sales and measurement equipment for the ferro and non-ferro industry. Since more than 5 years, I work as product manager for Bertel Technologies and then mainly for products for metal producers. I usually try to get out to meet with sales representatives and end customers as often as I can. I do this mainly since I know that good products are designed from knowing the customer and his needs. Lately, I have for obvious reasons not met with so many customers in real life, but still many over Skype, Zoom and Teams. So let's have a look at the agenda and what I have prepared for today's webinar. First, I would like to mention a few words about Berthold, and then also about the basics of a radiometric mold level measurement. This is what I call background here. Then we take a look at statistical variation and response time of a radiometric level system. We look at how to calculate the expected theoretical precision. Once we have the theoretical precision, we would like to verify this in reality. If we have an old caster, we might also have some issues with crosstalk. This we will address in this bullet point. In the optimal source session, we will take a look at possible source elements and also their pros and cons. Then what about electromagnetic steers and brakes? Do they affect us? Here we will discuss how to find that out and how to battle that if we have some influence. Then we will talk about how we can find out if casting powder is having an effect on our measurement and also how to minimize that. And then also how can we suppress mold oscillation influence. And as we mentioned before, there will be a question and answer session in the end, where I will do my best to try to answer your questions. So a few words about Bertel Technologies. Bertel Technologies is a German-based company with headquarters in the southwest of Germany, actually quite close to the French border. As you can see in the picture, where it's marked with a red dot. Berthold is a family-run company with about 350 employees worldwide. We see ourselves as the leader of process measurement equipment based on radiometry and we have been doing this type of measurement for more than 70 years now. Globally, we have more than 20,000 nuclear gauges in operation. And where are we? Bertel is quite active in a few areas, and our process measurement equipment can be found in, for example, refineries. And here we have customers like Shell, ExxonMobil, Total. Also in the chemical industry, we have customers like BASF, Dow, Eastman, SABIC. Obviously, we have products for the steel industry, mainly for continuous casting, and customers like ArcelorMittal, POSCO, ThyssenKrupp, just to mention a few. And we're also present in the mining industry, and here we have customers like BHP, Bilton, Rio Tinto, Vale, and Anglo. And also many other areas like oil offshore, coal gasification, pulp and paper, sugar mills, wastewater. So let us cover the basics of a radiometric level measurement. So we first take a look at the three main parts of a system. And the first part is a radioactive source. I'll try to show you here. And the second part is the detector. This side here. On the other side of the mold here, this is a mold, and inside the mold I have tried to make a drawing of some liquid steel. And the last part is an evaluation unit. The evaluation unit is not present here in the picture, but that would be connected to the detector and receive the pulses from the detector. So this is how the setup looks like. Then the basic principle of a radiometric level system. The source emits gamma radiation, whereof at least a part of the radiation hits the detector. As seen here in the picture, radiation comes from the source. Part of the radiation is attenuated inside the steel, but a part of the radiation is also reaching the detector. Once the medium, here steel, in the mold change, more or less of the gamma radiation will reach the detector. A high steel level will reduce the gamma radiation at the detector, and a low steel level will allow for more gamma radiation reaching the detector, which I hope you think is obvious. If we have a low level of steel, more radiation will reach the detector. If we have a high level of steel, less radiation will reach the detector. For each detected gamma ray, the detector will send an electric impulse to the evaluation unit. The evaluation unit will then convert the number of pulses per second into a level based on the active calibration curve. So here is an example of a calibration curve for an evaluation unit. And if we look at here the zero level, that's zero level in the mold, we have 10,000 counts. So we have more counts when the mold is empty. When the mold is full, 100%, we here have 1,000 counts. And these are the two extreme points that we use for our calibration. Once we have the full point and the empty point, we make a straight line between these 2 points and get our calibration curve. And this calibration curve is then used by the evaluation unit to send out the 4 to 20 milliamp signal, or the mold level signal on any interface. Now let's take a look at how statistical variation and selected response time affects the relative deviation. So gamma radiation is generated by statistical distributed decays of radioactive materials. This means for us that even at the constant mode level, the output signal undergoes statistic deviation. The relative size of this deviation, or standard deviation, can be expressed using the following expression. I will soon explain this expression a little bit more. And here you see we have the two unknowns where n equals impulses per second, and where tau, this is the tau, equals time constant. And if you look at the expression, on this side we have the relative standard deviation. On this side we have an expression where we have the two unknown, the n and the tau, in the denominator. And that means when these two factors are getting bigger, our relative standard deviation will decrease. So more counts per second and the longer time constant will decrease our standard deviation, or our relative standard deviation. In other words, many pulses and a long time constant will give us a smoother mode level signal. Now, let's take this discussion a bit further and also add some more variables. We now include also the total measuring range, which I call LT here. This is the range in the mold where we measure the mold level. Then also the casting set point. This is the point where we would like to have our casting level. And then also the empty count rate, and empty, which equals the number of pulses we get when our mold is empty. If we use this expression from the previous slide and then rearrange it, we can actually get the following expression. And this expression is explaining how big our deviation will be on our casting set point. So how many millimeters deviation will I have on my casting set point when I have n empty number pulses per second, and when I use a tau value, or a time constant value? And let us populate this expression and see what that means for us. If we use some quite normal conditions for a small billet cast, we can use n empty 10,000 counts. We have a tau value here of 0.8 seconds. We have a total measuring range of 150 millimeter and a casting set point at 75% of the total measuring range. If we put these values in the formula above, we can then calculate our deviation. And here in this table, I've calculated the deviation for 3 different sigmas. And I will talk about sigmas a little bit more soon. But as you see, for 1 sigma, we have a deviation, or expected deviation, of plus minus 0.6 millimeter. And twice for 2 sigmas and 3 times for 3 sigmas. And what does that actually mean for us in reality? Well, this actually means that if we go with 1 sigma, that means that 1 sigma it's covering, say, 68% of the time of our measurement. So in 68% of the time, we will have a deviation less than 0.6 plus minus 6 millimeter. If we look at 2 sigmas, that corresponds to 95% of the time, the casting time. We will have a deviation of plus minus 1.2 millimeters. And 3 sigmas, which corresponds to 99.7, which I would say is all the time. We will have a deviation less than plus minus 1.8 second. So By having this expression here and knowing some values about your caster, you're able to calculate your theoretical deviation. And again, as you see, once you have more pulses, you get a better or less deviation. In order to help you to calculate your theoretical deviation, we have put together a simple Excel tool for you. And this tool is using the expression that you saw on the previous slide. Here you have 4 input windows. The first one is measuring range, the total measuring range. The second one is the total number of counts per second. Then you have the time constant, which is the tau value, and then you have the set point, your casting set point. If you input values in these 4 fields here, you will get output in the fields down here, and you will have output values in millimeters, in percentage, or in CPS for 3 different sigmas. I think it's probably wise again to stress the golden rules for high precision or accuracy for a mode level system. Again, the higher empty count rate you have, the better your precision will be. That means if you think that you have not good precision enough for in your mode level system, the easy way would be to have use a new source or a more active source than you're currently using. That means with more counts. Another thing to know is that when you have a higher time constant or a longest time constant, you get a smoother mode level signal, but you will slow down your response time. For a fast caster like a billet caster, you normally work with 0.8 seconds as time constant, but for slower casters like big blooms or slabs, you can work with a longer time constant, let's say 1.2 seconds or even more, in order to get a smoother mode level. Which is probably also interesting to know is that the higher set point improves the precision of the system. A mold is usually designed to have a certain set point for the casting level. However, if you're casting on a higher level, your precision will be better using a radiometric mode level system. I've been asked many times by customers, when do I need to change my source, Albert? And this question is not simple to answer because it actually depends. It depends on the customer and what they expect. I have seen casters using the same source for more than 20 years and casting with sources below 1000 CPS still working. But this is nothing I would recommend. So when it's time to change the source, it's actually a matter of the casting speed and the required precision, that the customer required precision. And with this sheet, you can actually calculate for yourself when you would like to change source. So now we have calculated our expected deviation. How do we verify this in reality? And the way we recommend to verify the deviation of a radiometric mode level system is first we prepare a mold in casting position with source and detector. Then we calibrate the system, performing 0 and 100% calibration. We place the calibration block inside the mold at casting level. We open the source and chart the mode level signal for some minutes. Then we compare the charted mode level signal with the calculated signal, calculated deviation, and their deviation should match, which they will. With this procedure, you will know what deviation your mode level system operates at. But in case you find out that you have a mode level deviation that is more than expected from your theoretical calculation, you should be looking for deviation in other sources. Other sources should be examined, like the level control system. For example, the PID regulation of your level control system might not be optimized for the quick response time of the mode level system. Then you also have the flow control system, where you can have clogging in the flow control system, which will affect your mode level signal. Then you also have the possibility of having mechanical issues in the strand withdraw system. Some could be called bulging. Some years ago, I was contacted by a steel plant chief telling me he had some serious issues with his mode level system. I asked him for data from his EBA system, also from his PLC, and asked also for along with the log files from our mode level system. When I looked at the data, I could confirm that he had serious issues with his mode level control, but not with his mode level measurement. The mode level system only measures the level in the mold, but it doesn't control the level in the mold. Here is a movie showing the mold in this plant. This was a new thin slab caster, and if you look to the left of the SCN, that's the glowing pipe there, you will see the level is pumping periodically. So if you look in this area here, you will see the level goes up and down. Let's see if I can start it. And obviously, this pumping was seen on the mode level signal, but it was not created by the mode level measurement. But the customer, of course, thought that the mode level measurement was the problem. So the problem here was actually bulging. And bulging comes from uneven pressure from the rollers below the mold. And this can cause the steel level in the mold to pump like this. Quite some old casters were designed with a radiometric measurement for the different strands in a row. Modern casters are designed with level measurement for each strand being parallel. So here is a drawing of quite an old old caster, and here is one source, the mold, and one detector. Second detector, mold, and second source. And then this sequence repeats itself. Here, one source, mold, detector, detector, mold, source. This is obviously not the best layout or design of a caster, because there is quite a big risk for crosstalk between these two strands. If you look at the arrows here, you see in what direction the sources are facing. And you see where I have noticed, where I have put the crosstalk bubble. You see the problem here, because this detector will detect radiation from this source going through the mold, but also radiation from this source going through this mold and passing this detector. So as you can see, there's quite a risk for crosstalk for strand 1 and 2, and also for 3 and 4. Strand 5 is much better off. This actually means that the mode level measurement of the strands are not really independent, but affected also by the steel level in the neighboring strand. This is of course not good for measurement precision. The way to handle or to reduce crosstalk is to add high density material so that each detector is only affected by its own source. So here in the picture we have added shields between the two strands that were crosstalking, and these shields should be made of high density material because high density material attenuate radiation better than low density material, and that could be lead or steel or any other high density material. So we have found out that we have crosstalk between some strands. What do we do? Yes, as we said, we need to add high density material between the strands. If we look at the following table, we see some values for the half value layer for this cobalt-60 isotope. This means that the table shows the amount of material for different material needed to reduce the gamma radiation from cobalt-60 with 50%. So we have a source, which is cobalt-60 here. We have different material, concrete, steel, lead, tungsten. And they also go from concrete to tungsten in density. So concrete has the lowest density and tungsten has the highest density. If we take 60 millimeters of concrete, that will reduce the gamma radiation from cobalt with 50%. That's why it's called a half value layer. Steel, you need about 22 millimeters to reduce the gamma radiation with 50%. Lead, you need 30 millimeters, and tungsten, you need about 8 millimeters. This also means that twice as thick steel plate with half the radiation one more time, meaning a reduction to 25%. So if we have a steel plate of 22 millimeters, that will reduce the radiation to 50%. If we have a steel plate that is 43 millimeters thick, that will reduce the radiation 2 times. So first from 100 to 50 and from 50 to 25%. Tungsten is here mainly for reference purposes. It's a pretty expensive material, and if one can use steel or lead, that is usually preferred due to the cost of tungsten. For radiometric mole level application, there are, to my knowledge, only 2 elements being used. These are cesium-137 and cobalt-60. Berthold always recommends cobalt-60 for mole level for obvious reasons. Here a table which shows the properties for the 2 different elements, cesium and cobalt-60. If we look at the specific energy, we see that the gamma ray from cobalt-60 has about the double energy compared to a gamma ray from cesium. So 660 here, and almost you have 2 different levels here, which are about the double of cesium. This means that the higher proportion of the gamma radiation makes its way through the mold wall and hit the detector. And this is the reason for why you can use much less radioactive material for cobalt compared to cesium. So if you go with cesium source, you would have to have a much higher activity on the material, because only less gamma radiation will make the way to the detector than if you were using cobalt. And since cesium has less specific energy, casting powder will attenuate the cesium radiation from cesium to a greater extent than from cobalt-60. For cesium, the physical form is ceramic points, so it's not a continuous source. There are cesium embedded in ceramical points. For cobalt, it's a metal wire, which is continuous. Cesium is also much more expensive than cobalt. And if you calibrate using a cesium source, you will not get a linear response curve. That means you cannot do a 0 and 100% calibration and get a linear curve between those. For that you can do with cobalt, because that is a continuous and linear source. We also see that the half-lifetime for cesium is much longer than for cobalt. However, we design our cesium's cobalt sources for a lifetime between 10 and 15 years. And this is normally above the national recommendation. That means even if you have a half-lifetime of 30 years, you're not allowed to keep the same source for 30 years. Now we have calculated our theoretical precision and also verified that in reality. We also know that cobalt-60 as a source is our best source selection for mole level measurement. Now it's time to find out if we do have any noise from electromagnetic stereos or breaks. And electromagnetic stereos and breaks, they operate with very strong low frequency or non-frequency electromagnetic fields. Such electromagnetic fields can cause the flying electrons inside the detector to deviate from its trajectory, causing lost counts. So the way we recommend to find out if your radiometric mole level system is affected by a stereo break is very straightforward. First, you prepare a mold or a system at the molding casting position with source and detector. Then you open the source and chart the mole level signal for some minutes. You turn the stereo or break on and chart the signal for some minutes. Then you compare the deviation for the two charted signals with stereo and break turned off and on. In case you have a difference between these two signals, or you have a negative influence from the field from a stereo break, there are actually two main options for you to battle this. The first option would be to change mode level detector to a detector that is silicon photomultiplier based. This is a new technology. It's only offered by Berthold. And the detector based on silicon photomultiplier is totally immune towards electromagnetic fields. Another way would be to increase the electromagnetic shield around the detector. That would mean adding more ferromagnetic steel around the detector. Of course, not covering the window of the detector, but covering part of the body of the detector. So how to minimize the effect from casting powder on the mole level signal? First, we have a picture here on the right. This is the mold wall. Between the mold wall and liquid steel, we have a slag film that is molten casting powder that melts and goes down here. And on top of that, we have mold powder. And in here we have liquid steel. Mold powder or casting powder has a density of about 0.7 to 0.9 gram per cubic centimeters, which corresponds to about 1/10 of the density of molten steel. For small molds, approximately 1 centimeter of casting powder will correspond to 4 millimeters of steel pushing down the steel level. That means if you add 1 centimeter of casting powder in your mold, you will get you will have a reading of plus 4 millimeters on your mold level system, and then the regulation and the control system will push down the steel level about 4 millimeters accordingly. For large molds, the powder effect becomes bigger due to the increased pathway for the radiation in the powder. If you have a really big mold or really big bloom, let's say a cross section for 500 millimeters, a radioactive or radiometric mold level system cannot really distinguish between powder and steel anymore, and will see the powder as steel. But this we try to solve by not shooting across large molds. I mean, trying to use corners and so on to decrease the pathway for the radiation. And as I mentioned before, using cobalt-60 as a source will provide a much less powder-influenced mold level signal than for using cesium-137 as source. For a recent product that we have released, we have used the difference in radiation attenuation between casting powder and steel, and we can now offer a product that can measure both the steel level and the powder level simultaneously. That means you get a signal showing this level here and how thick your powder layer is, and also the true steel level. So you get two continuous and true levels from that new product. Another thing I would like just to mention is that the slag film here between the mold wall and the liquid steel is lubricating the steel, but it's also acting as an insulating layer. This means that measurement equipment that are trying to measure the steel level by looking at the temperature profile in the mold wall cannot be quick enough for small formats, because they will always have to wait for the temperature profile to move through this insulating layer. So what about the mold oscillation? Doesn't that affect my mold level measurement? Well, the answer is it depends. For a mechanical installation where the mold level system oscillates with the mold, some influence can occur on the mold level signal. This is mainly seen for oscillation frequencies below 3 Hz, which equals 180 revolutions per minute, which normally corresponds to bloom or slab formats. For higher frequencies, the effect is cancelled out. So that means for a billet caster, this effect is usually not seen. In our evaluation unit, we have a built-in functionality for filtering out oscillation frequency without reducing the system response time. This function has been tested for some time now, but it hasn't so far been described in the user manual. In case you have a need for it, please let us know and we will help you to get that set up correctly. And if you look at the graph here to the right, the blue signal here, that's the unfiltered signal from mold level signal, where you can see you have oscillation on that signal. And after we have enabled our oscillation filter, we get this orange signal, where it's actually only carrying the level information in that signal. But only for this is only interesting for people running casters below 3 Hz or up to 3 Hz. Otherwise, the oscillation effect is cancelled out. We have now covered the presentation and reached the question and answer session. I would also take the opportunity to mention that in case you have an interest here, would like to find out more about what we talked about or take a deeper look, we have a white paper on our homepage which you can download. I'm now happy to try to answer your questions to the best of my knowledge. Carrie, have you got any questions from the audience?
There's one question now.
Mm-hmm.
Have you ever had to shield an EMS directly when the interference is affecting more than just the detector? Do you want me to read it out?
No, I'm thinking. We have had occasions or installations where the EMS was affecting the detector. That is usually only our is in our interest, and in that case we had to add some ferromagnetic steel around the detector, but we are not really concerned about other effects from the EMS. So I would say no to that question.
Okay. I have a further question. Do you recommend a 9-point calibration for funnel molds?
I would say I would recommend a multiple point calibration for funneling molds, especially around the casting level.
Okay, that's all so far. There's another one. Is there any industry standard for precision deviation, or is this entirely dependent on the company and application?
The deviation that we have is based on on common physics. It's nothing we can change. I would think that Berthold is the leader here and has equipment that is providing the least deviation of the other from all providers, but we all have the same physics to rely on.
Okay. Would a 2-point calibration of empty mold and shutter closed be adequate for linear calibration?
I would say yes, because you are not, or the customer or the users are not really interested in having a good precision down in the mold at 1, 2, 3%. They're only interested in being able to start the caster. So I would say yes, that would be okay.
Okay, and then is it reasonable to shield the EMS directly when the detector cannot be shielded?
I cannot really answer because that could affect the EMS. That is actually a structural thing. If you have a lot of ferromagnetic steel added around the stereo, that can affect the electromagnetic field of the stereo. So that I cannot really say yes to.
Okay. There's another question. I'm not quite sure. Has the filter... Could the filter be applied to an old system? I'm not quite sure.
The filter cannot be applied to our old evaluation unit. That's the LB352, if that was the question. Our but for sure for all our 452 units.
Okay. Where is the new detector being used, detecting both metal and powder depth?
We have a couple of customers for that. We have one in the United States. We have a commissioning happening this month, so it's coming out there. It takes a while to get from product introduction until it's up and running in a new steel plant.
About the sensor capable to detect also powder level, are you talking about ConGauge developed in cooperation with Concast?
Yeah, this was the product I was referring to, yes.
Okay. Is there a difference in attenuation comparing liquid steel versus the solid calibration plates?
No, because the steel thickness, or I mean the distance or the mold is so big, so the liquid steel or a solid crystallized steel or solid steel will have 100% attenuation. So there's no difference.
Okay, you mentioned a newer technology to detect mold powder. Is this effective for larger applications like blooms? Also, does a setup on the corner of the mold make it more effective?
It can be used for all formats. And depending on the size of the mold, one have to look at where to place the detector.
Okay, that's all so far in the chat. There's no more in the question and answers. Okay.
Then I would like to thank you very much for your time and interest. I hope you think it has been worth the time and that you learned something new in this webinar. And I would also like to thank you for all the good questions. Should you have any additional questions, you are of course welcome to contact your Berthold representative or me directly. And I would like to wish you a great day and successful casting. Thank you.